In this lesson, we will review properties of logs and then learn about some calculus with logarithmic functions. Specifically, learn the derivative of the exponential function to the base e, learn the derivative of the natural log function, learn the derivatives of exponential and logarithmic functions to any base, and also to learn about logarithmic differentiation in general. So let's get started. Again, I'm starting with a review of property of logs because from my past experience, I find that doing calculus with logarithmic and exponential is not that bad. It's the properties of logs that students are weak on. So taking some time to do that up front, I think will pay dividends later on. So let's take a look at the properties from algebra. Okay. First of all, a few basic before we even look at the properties, natural log of x, abbreviated by ln of x, and that represents logarithm to which base? You may recall from your algebra classes that that represents logarithm to base e. And what was e in the first place? The value of e is 2.718. It's a non-repeating decimal. It's an irrational number. And we're going to learn in this session actually why e is called the natural base, because again, natural log is base e, and that's called, all along in college algebra, you call that natural logarithm. And why natural? It doesn't look like a natural number, does it? So we're going to learn about that later on today. As it turns out, this base is the easiest base with which to do calculus. So that's why it's called natural log, and we're going to see why in more detail. So let's remember these properties of logs as we see on the screen. So natural log of a plus natural log of b equals natural log of a times b. And this could be log to any base. It could be log base 5, it could be log base 10, and if it's log base 10, it can also be written simply as log of x. So I could have the same property here that says log of a plus log of b equals log of a times b. And that's sometimes referred to as sum of two logs equals logarithm of the product. The next property states difference of two logarithms equals logarithm of the quotient. So ln a minus ln b equals ln, or natural log of a over b. Then another property of log states natural log of a to the r equals r times natural log of a. So you can bring the power down. You don't subtract one or anything. We're not differentiating. You can only do this when you're dealing with logarithms. This rule only works with logs. So if you have an ln or log to any base, you can bring the power down. And property number 4 reminds us that e to a power, like e to the x function, and the natural log of x function, that these two are inverses of each other. As you can see in this graph, y equals e to the x has this graph, y equals natural log of x has the bottom one, and they are symmetrical with respect to this dashed line, that the line y equals x. And anytime you have that situation, you know that you are dealing with two inverses of each other. And the meaning of an inverse function is if you apply one after the other, you get x, or you get back what you started with. So for example, if you have the square root of x squared, and assuming x is positive, you would end up with just x. So if you apply square root right after you apply the x squared function, the two of them undo each other. So similarly, let's take a look at property number 4. When you have e to the power of natural log of x. So first you applied natural log, then you just took e to that power. The two of these will undo each other, and you will end up with just x. And one more property, actually 2 more, and then we'll be able to do some examples. Okay, property number 5 shows us how to get rid of a log. So if you have an equation that has a log in it, it shows us how to write that in exponential format. So logarithm to the base a of x equals y. If and only if, that means you can go this way, also backwards. Okay, so to get rid of a log, the way you would write this is a to the power of y is equal to x. So that's what you see on the side. A to the power of y is equal to x. And another way to see this is You can exponentiate both sides. Exponentiate this side and exponentiate that side. Now a to the log of a, they're going to cancel each other and you're going to get x. And on the other side you have a to the y power. So that's another way. If you don't want to memorize the rule, just as long as you know that exponential function with the base a and logarithmic function with the base a are inverses of each other, you can always get that from that knowledge. And property number 6 shows us how we can rewrite a given expression in terms of any other base. This is sometimes referred to as change of base rule. Log to the base a of b equals log of b over log of a. Now in this situation, what is our new base? If I didn't write any base, that's understood to be base 10, right? And this is also equal to natural log of b over natural log of a. Again, if I didn't write any base, that's base e. And I could go on and on. I could write many different bases, the same expression. So the rule is saying if you have logarithm to any base a of b, and say you want to switch it now to a base such as base 2, you could have log base 2 of b divided by log base 2 of a. So this is our change of base formula. And a few other simple tips about logs. So anytime you have log base a of a, that's going to be equal to 1. A very simple checking mechanism is, again, get rid of the log by doing a to the first power. That should be equal to whatever you have here, and that is indeed a. And some people will define a logarithm saying a logarithm represents the power that you must raise the base to get this quantity. And that power is really 1. You raise a to the first power to get a. Again, there are many ways to see that, but it's good in general to know that logarithm base a of a is always going to be equal to 1. So as long as this number matches that value over there, then you are going to have 1. So for example, natural log of e, that's logarithm base e of e. For the same reason above, this is also equal to 1. Okay, natural log of 1. And the answer is 0. And if you think about it, there's a hidden base of e here. So e to the 0 is going to be equal to 1, right? And these are some simple ones that you shouldn't really have to use a calculator. In my opinion, you should know how to get these without a calculator. Know that ln e is 1. Know that ln 1 is 0. And what about something like ln e squared? In that situation, we can apply property number 3, which tells us you can bring the power down, right? Bring the r down. That was property number 3. So bring the power down. And here we're going to have 2 times ln of e. And we know ln e is 1, so the answer will be simply 2. Same idea here. The answer will be 3 because it will be 3 times ln e. Ln e is 1. The answer is 3. This one over here, any guesses? If you said 2, you were correct because base, if they didn't give us a base, it's assumed to be base 10. So you can bring the power down and you'll have 2 times log base 10 of 10, which we know is 1. So the answer is going to be 2 times 1 or 2. What about this one? Log of 10 to the negative 1. Again, no base written, that's base 10. The answer is negative 1. Now for something like this, log base 2 of 3, there's really no way of simplifying that. You cannot even find this on the calculator easily unless you do a change of base formula. So you can change it to, let's say, base 10. You could say log of 3 over log of 2. And now on your calculator, you have a log base 10 key, and you can enter, log 3 over log 2. You can get a decimal value now using your calculator. And log of 25, no problems there because this is base 10. Again, we're not going to be able to simplify it by hand because 25 is not a perfect 10 to a power, but we can do this one on the calculator since there's base 10 key already in our calculators. We can just type in log of 25, and I'm getting roughly 1.398, or very roughly 1.4. So I hope logarithms, the properties are starting to come back to you. I know being in calculus, you have seen these before, possibly in algebra, or maybe even in pre-calculus. Now let's do a couple examples before we move on to doing calculus with logarithmic and exponential functions. And you're going to see it's actually easier than the properties of logs. Calculus with exponentials and logs is easy. You will see that in a few moments. Okay, so let's solve this example. How long would it take for $2,500 to grow into $4,750 at 7% continuous compound interest? And for this one, I need to remind you of a formula from algebra. Continuous compound interest was A equals P times e to the RT, or A equals PERT, as some students refer to it. Here, P is your principal, R is your interest rate, T is the time in years, and A is your accumulated value. So here, we want our investment to grow into 4750, so that's our accumulated value. The amount you're investing is P, and interest rate in decimal form is 0.07. The only unknown is time, and they want to know how long. So we'll be able to figure that out when we solve for t. So let's plug everything that we know in here. So accumulated value is 4,750 equals the principal, or 2,500, times e to the RT. R is 0.07 and t is the unknown. Okay, notice that the unknown here appears in the exponent. Now, if I had an equation such as t to the third equals to 64, how would you solve for t? Well, you could take the cube root of both sides, right? So you could take the cube root of both sides and you could get a 4, t equals to 4. But when you have something of this form, 3 to the t equals to 64, now the question is 3 to which power is 64? So, 3 to the second power is 9, 3 to the third is 27, 3 to the fourth is 81. So somewhere between 3 and 4 is the answer, but we couldn't really do a cube root here. That is really not the only time you do a cube root is when you have a third power and you're trying to get rid of that, so apply the 1/3 power or cube root. But when you have a power of t, the only way we know how to solve equations like that is applying logarithm to both sides. So same idea here. The unknown appears in the exponent, and the only way we can solve that power, the unknown in the power, is by applying logarithms. So just since I started this one, let me just go ahead and finish this. If you apply logarithm to both sides, or I'm going to do natural log, so natural log of 3 to the t equals to natural log of 64, and then here you can bring the t down, so you have t times ln 3 equals ln of 64. Now divide both sides by ln 3, and you will find the answer. At this point, you're going to need to use a calculator and just go and enter ln of 64. Make sure you close the parentheses. After that, division by ln of 3, close the parentheses and press enter, and you'll get like about 3.8. We did expect somewhere between 3 and 4, right? So 3.79 to be more exact is the t value there. Now in this situation, for our original question, before we can apply natural log, we need to isolate the exponential term. So you would divide, first of all, both sides by 2,500. So let's do it. 4,750 divided by 2,500 equals e to the power of 0.07t. So let's simplify the left-hand side. 4,750 divided by 2,500 is 1.9, equals the right-hand side from above. And now apply natural log to both sides. So we do natural log of this side equals natural log of the right-hand side. Now we can find ln of 1.9 on the calculator, which is 0.64 roughly. 0.64, and on the right hand side I can simplify using property number 3. You can bring that power down, right? That was r in the property, so here our r is 0.07t times natural log of e. And what do we know about natural log of e? As we reviewed in the previous slide, it is 1. And now it should be very easy to solve for t. Just divide both sides by 0.07. So here we have t equals 0.64 divided by 0.07. So let's do that. 64 over 0.07. I'm sorry, 0.64 over 0.07. And there we're going to get 9.1 roughly. So t equals to about 9 years. So about 9 years it will take for $2,500 to grow to $4,750 at 7% continuously compounded interest. And we were reminded in this example that logarithms is really the only mechanism that we have to solve situations like this where the unknown appears in the exponent and it's not easy to guess the answer. In that situation, we apply logs to both sides. Okay, here are a few more examples. Like something like logarithm of 1,000. How would you simplify that? We've already done some of those. I'm just going to do one of these. Say log of 1,000. Well, that's the same as log of, move over here, log of 10 to the third. And if there's no base, base is assumed to be 10. So based on what we did in the previous slide, what should this be? If you said 3, you were correct because you bring the 3 down and you go from there. 3 times log base 10 of 10, so that's 3 times 1 or 3. Okay. A few more simple examples to refresh our memory about logarithms, and then we're going to be ready to do calculus with these. Let's take a look at this slide. For example, if you have natural log of x is equal to 3, how would you solve for x here? You could use one of our properties. This is property number 5. That tells you how to get rid of a log. So if you have a log, so you say this base to that power equals to this quantity, so a to the y equals x. So let's apply property number 5 for this question. So the unknown base is e, so e to the third equals x. So e to the third equals x. Or if you remember that you can apply the inverse function to both sides. E to the ln, it will cancel and you'll get x. And then e to the 3 will be the answer. So x equals e to the 3. Over here, the hidden base is 10. So again, let's do 10 to this entire power equals 10 to this power. So 10 to the second power is 100. 10 to the log base of 10, they will cancel each other. They're inverses. So we have x minus 3 is equal to 100. Now add 3 to both sides. So x equals 103. A few more examples. How would you do this one? Well, before you can get rid of the log, you need to get a single logarithm. And for that, let's use property number 1. The sum of two logs is logarithm of the product. So in this situation, log base 2 of the product of x times x minus 6 equals to 4. Now, since we have a single logarithm on one side and a number on the other side, we can use property number 5 again, or just do exponentiation. 2 to this power equals 2 to that power. 2 to the log base 2 will cancel. X times x minus 6 equals to 2 to the 4th power. And if we expand this a little bit, x squared minus 6x, 2 to the 4 is 16. And we can factor this. So negative 16, let's say that's negative 8 times positive 2. because the product of those two is negative 16, and the inner plus outer will give you the negative 6x. So it looks like there are two solutions, x equals negative 2 and x equals to 8. However, of those two, we can only accept this one, because if you take the negative 2 and plug it back into this equation, you're going to get a negative value, and the logarithmic function is not defined for negative values. Same thing here, log of negative 2 would not have been defined, so we reject this one. So this is not an appropriate solution. We call those extraneous solutions, so there's only one in this case, x equals to 8. Okay, and then these are the last two examples about reviewing properties of logs, and then we're going to start with the differentiation of logarithmic functions and exponential functions. Let's take a look at this one. Write this given expression as a sum or difference of logs. So we're going to use properties number 1 and 2, but this time backwards. It's given to us a quotient. First, let's write it as a difference of two logs, which will be natural log of the top minus natural log of the bottom. And we can further break this one apart. Natural log of a times b is ln a plus ln b. So break that apart as a sum. And finally, there's one more thing we can do with those powers. Property number 3, we can bring each of those powers down, right? So here we have 6 times natural log of x plus 4 times natural log of y minus 8 times natural log of c. So that's how we can simplify this. And the beauty of this approach is in a few minutes, we're going to learn how to differentiate the natural log function. But if you have this messy expression, you're going to need to use the quotient rule, the product rule. It gets very messy. But if you can first simplify it, then taking the derivative will be very easy, because you can take the derivative of each piece one at a time. And some of you may look at this expression, and from there, without showing these two steps, may be able to show this last step right away. If you can do that, that's perfect, that's fine. And if you don't feel comfortable, by all means, show the other two steps as well. So we're doing something similar here on the last example. Now we have 3 separate logs, and our job is to combine them into a single log. Okay, so let's begin. First, we need to get rid of all these powers by putting them at the top. So this can be written as log base 2 of x plus 1 to the third minus log base 2 of 2x plus 1 to the fourth plus log base 2 of 3x minus 1 to the 5. And now anytime you see a difference, remember it's going to appear as log of the quotient. Anytime you see a plus, that will appear as logarithm of the product. Like if you wanted to, you could put this one and plus that right next to each other. That's going to give you a log of a product. That will give us log base 2 of the product of x plus 1 to the third times 3x minus 1 to the 5. And then at the end, you would have this term which says minus log of something. And again, we know log A minus log B gives you a quotient. So that quantity will appear in the denominator. 2x plus 1 to the power of 4. And if you'd like to practice that some more, I think you have some examples like these perhaps in your group activities, or there's a handout that I believe I may have passed around in class. So there'll be more examples, you can practice. But ultimately, what I want you to be able to do is really not simplifying logarithms, but doing calculus with logs. So let's take a look at what we mean.